Welcome back for the third tutorial. I'm just gonna go on the pendulum example and see how we can control it when we apply a torque on it, which is basically the second step. So let's see what we have here. Now the dynamics have changed because let's say that we have like a force, a torque actually, or like somebody that's like pushing the massless bar up to a desired position because we want the pendulum to behave in a way that is desired to us. So in this case, it's easier to solve the problem by the torque equilibrium, by summing all the moments. And we can see that indeed we have the mass. We're going to do the equilibrium around this point, which is really easy. It's where we apply the momentum to the system. And we have indeed mgl sin theta of this force here with arm L. The same is happening for the inertia, the same R minus, in this case, the torque, which has to be 0. The inertial acceleration does not change, but now since we have a torque, we cannot simplify the mass, and we arrive to the following ODE, which is the ODE for the torque control pendulum. And indeed, as we can see, while before we were able to simplify the mass, now we are not. So the mass, of course, the bigger the mass, the harder it's going to be to move it in a desired location. And I've decided to get 0.2 kilograms as the mass, just because. And let's see how it goes. So let's go back to where we left last time on another constant. I realized I went kind of fast in the last video, but I'm also like, hey, it's a video. I can pause it and like just write me a question if you don't understand, and I will do my best answering you in the most clear way I can think of. So first of all, we have to change our dynamics. We have to change our dynamics because we have the torque. And let's start with the Simulink on base one. Let's move it down a little bit. So now I'm gonna add some inputs in port number, let's say 2, then another one, port number 3. I think that's all. I think that's all. So what we have to create here this equation here. So it's theta, a part that we already created, and we have to add this component here, which is tau, which is our torque, over m L squared. So let's go back and divide. So we have tau, which is a multiplication, over m, so division, over L squared. Let's just do division. So I want names because it's going to be easy to connect it after. Let's say this is mass, m is fine, and this is the torque, tau. So I think I have in the torque, tau, over the mass, and then here I keep the length over the length square. Here we go. However, now this gets added. Let's go back to the equation, to this component here. So I want a sum block, which is gonna be, I can do plus, minus, and get rid of this gain here. So it's gonna be minus, it's gonna be plus, and this is my theta dot now. my God. Nice. Velocity, position, save, and that should be it. So I'm asking for tau and I'm asking for m. See, we haven't written what is this. Try to keep order on your code. You will have a nice time if you do. So this is the mass. Now, I actually do not know if I've taken the feedback control class, but as engineers, you should know what a PD controller is. We're gonna, even in the class and in the final project, you're only gonna use a proportional and derivative controller. You're not gonna use the integrator part of a PID controller. So, and that's basically also why I'm choosing this example, because it's easy to simulate a PD controller. And I think that's what I'm gonna do now. So let's say a controller, a feedback controller, works on look at the position of the system as now and decide how to behave compared to that. So now we just want to bring the system that is starting with 0 velocity and phi and position of phi over 3. We want to just bring it back to equilibrium at the bottom. So like 0 position and 0 velocity at the end. I want like for it to stop in the most easy way. So let's quit. Let's start it. Let's sound. Let's say plus plus. Control E. And then this is gonna be my torque. I want to do something here. I really want to work with the system. Let's move this down. Easier. Let's go back here. Control E. Control E. So this is the actual position I have. Let's say this is the actual velocity. We need gains for the feedback. And let's say -2 for the first one, -2 for the second one. You're gonna see better what we're doing now in a bit. The gain are negative to keep the poles of the system in the left part of the plane. And so basically here, this is our controller is looking at the position and the velocity of the mass, and like with the given gains, decide how much torque. Here is going to be our torque to apply the system. And then usually this is only a law, and there's going to be another block that is to create, which is like the actual actuator that usually gets the law, and you are going to simulate the hardware and of how much of the actual torque that's given. In your case, going to be to the spacecraft. Here, and we're just going to give like the required torque as is given directly from you are the hardware, and so basically this is just the PD controller block. And I think this is it. Let's go back. I said this is position, and that gets position. This is velocity, that gets velocity. Let's run it. And here we go. Look how beautiful it is. Indeed, we start at 0. A bit bigger. we start at 0 for the velocity and 3/3 for the position, and we can still see that the frequency has not changed. Like, the one is 0, the other is the maximum, and vice versa is kind of delayed, as we can see. Is because we are applying an external force on the system, which is delayed by the time step. But we see how the velocity and the position decrease in time, and at the end we get still equilibrium at the bottom, which is really nice. So basically, our controller is controlling the system to bring it in a stable equilibrium position. Indeed. Scope. Let's run it again. Let's analyze it. This is our torque, and we can see that it's fighting indeed the velocity, or like it's always fighting where the velocity is moving. Indeed, is moving negative. I'm gonna try to push it, and elsewhere in order to bring the equilibrium. Let's do the same with MATLAB and see if I did some mistake, because I'm just coding on the spot. To change my dynamics, so I go back here and see that I'm missing something. I'm missing not the mass, and I'm missing the torque. And this was, remember, plus tau plus tau over m over L squared. See? Let's go back to our blank model with the length. Of course, I need another input. Of course, not the integrator. Okay. Input, output, let's say 2 is fine. It's gonna be my mass. In port number 3 is gonna be my torque. Here we go. Let's go back. Indeed, now is asking for the mass. Here it is for the torque. It's gonna come. And now we have to do, I'm gonna call this PD controller simulink. Now we're gonna do the PD controller with MATLAB. So I want a MATLAB function. First of all, Control I is our feedback and comes back. Let's say it is tau, as it's asking for position and velocity. So tau is really easy, like a function is an equation, and it's gonna be, I said, 2 for both, minus 2. It's gonna be like position let's put this here just to be clear. Minus 2 is gonna help us for later. Position, because Because here, technically, it's your desired position and your desired velocity. But in our case, the V1 has desired position and desired velocity, something static, and we position 0. So usually the desired position and desired velocity, they talk to each other, and they have to be simulated as well, such that if it's something that you want to follow and behavior, position and velocity, they are connected. And so usually these two are other functions. And so right now I'm just gonna 0 and 0, which is easy, but at least for the math that there is behind it, you can have a better understanding. Actually, I might add a little bit later. On So as I said, it's going to be position and velocity. The output is tau, which is our torque. Let's run it. I think we're having the same behavior. Of course, I don't remember. Nope. Yes. Let's check. Let's check the torque. Usually you can give names even the scopes, and I strongly invite you to, especially when I have to grade. Nice. The system has been controlled. The pendulum is at equilibrium at the bottom. And that's it. I think is enough for now. Hopefully I was clear enough. I might add a little bit in the last tutorial. It's going to be really short, don't worry. So yeah, let's see for the last one. Goodbye.